Hello class. So this short video is meant to show where conservation of energy comes into our discussion of energy. Because at this point we learned about the idea of you do work on something and then that transfers energy to it. But what does it mean for us to try to say that by doing work on something we've stored energy in it, and that potential energy, that potential to do something that's stored, that allows the system to do something. So let's see where that potential energy comes out of the mathematics so that later on we can set up problems that make use of that. So as a reminder, well, when it comes to us talking about a system, we can say, okay, there are external sources of energy that are doing work on something. And all those external works are associated with many potential forces that are acting on a system, and all of those forces are acting over some distance, right? They're pushing through some amount of distance, and also based on how they're angled determines how much energy they're actually transferring to whatever object they're interacting with. So the first thing we said was, okay, so just generally speaking, the total amount of external work, if there's nothing like friction involved to slow anything down, is going to be directly equal to the change in the kinetic energy of an object. That is, I push on something, I'll have my chairs, oh, I do have a chair, it's out of the camera frame. You push on the chair, so I do work on the chair, and then it speeds up, or if the chair is coming towards me and I push against it, I slow it down. So I do work on something, I can change its kinetic energy. Then we said to ourselves, well, there is some situations where not all of the energy is actually going to make something go faster or slower, or so we can have, for example, friction. And so friction is a force that could be exerted on an object, but in the course of you moving things past each other and there being friction, naturally those objects, if you rub your hands next to each other, you can see how, as I try to move this hand relative to here, the friction causes them to heat up. And so that means that there had to be energy that's not going into the motion of my hands, it's going into heating up the surface of my hands, which means that energy is going into making the molecules move around instead of into making the object actually move. So we sort of said, hey, so now we can take, well, there's many different things doing work that potentially are doing work on my system. We pulled out one of them. We said, well, friction is only causing the surface to get warmer. It's not actually changing the motion of it. So we pulled friction out and we threw it over here and we gave it its own turn. Now the thing is, there's nothing that stops us from looking at other pieces of our system and then pulling out and saying, well, we want to isolate this other piece as well because maybe it's also not changing the motion of our system in a certain way. And to give an example of that, consider the following. So I have this weight here, and here, if I just say the source of the force is my hand, then I exert a force and I move this thing up, so I change the kinetic energy of this thing by exerting this force. But suppose I try to lift this with a little spring. So I have this spring here, and you'll notice that the spring has stretched, but I can still move this thing around. So I have my external force, my external source of work, which is the force of my hand, accounting for the change in the kinetic energy because it's moving around. I don't have to deal with friction, so we can ignore this term, but clearly the spring has stretched. And we know the thing about springs is if we stretch them, they can snap back, they can do things. So we've apparently done something to the spring, and we want to be able to account for that. So if the external source of work is just my hand, we have to account, well, what's going on with that spring? Why did it stretch? What kind of energy, did we store energy in it? And actually, the answer is yes, we had to store energy in it in order to stretch it. So in order to see what kind of formula comes out from pulling this kind of thing out, we can look at an example of an object that's just put at some height, some initial height, and then we let it fall and it reaches some new height. And we're going to examine this first in terms of the work that is done on it, and then in terms of the idea of this object has some amount of potential and kinetic energy. So, myself. All right. So just in terms of work, our idea of work here is that we're going to say whatever this object is, the object itself is our system, right? It's all there is. Everything else that exerts forces on it is outside of whatever the object is. So that means all of the external works that are involved, all the external forces that can act on it, are just going to cause its kinetic energy to change by some amount. Now in this case, because we're only going to care about this object sitting above the Earth, the only force that's going to be acting on it is going to be the force of gravity. So we got, based on this formula up here, we got that gravity is pointing downward. We got that the change, the displacement here, is based on h final minus h initial. We got that the direction of the force and the direction of the actual motion are the same way. In this case, both are pointing down. So that means this would be cosine of 0, so this whole thing, this term would be equal to 1. So this whole side here is now accounted for. This would be the amount of work that is done in moving this particle from here to here. And of course, because the amount of external work being done, well, there's no friction here we have to deal with or anything at the moment, that just means there's a certain change in the observed kinetic energy. Now what we can do is we can take this whole term and we can break this apart. We can say, now wait a second, there's an h final and an h initial here. So I can take this mg h final and mg h initial as two terms. And similarly, my change in kinetic energy is my 1/2 mv initial squared and a 1/2 mv final squared. So I can break that in half or into two terms. And I'm going to put all the initials over on one side, mg h initial plus 1/2 mv initial squared, and then similar for final terms on the other side. Then I can associate each of these terms with a corresponding quantity. Here, obviously, these are the kinetic energies of the particle. So if this is the initial kinetic energy, I'm just going to say initial K. And if this is the final kinetic energy, this is going to be final K. Then I look at these two terms here, and it's like, well, I don't know what these are at the moment, right? Unless I look into the future and I know these are the expressions for potential energy. But at the moment, I can just assign a variable to these. I'll just say, okay, well, this term and this term, they're clearly representing similar things because they have the same structure. I'm just going to call this UI, U initial, and I'm going to call this U final. Then, well, whatever this U term is and this K term, together, they must represent some total amount of energy, because that's the kind of terms we're dealing with here. We're talking about energies. So therefore, I can replace this entire combination of terms with some new term that just says this is the total initial energy of this system, corresponding to a certain amount of kinetic energy and a certain amount of what we'll call potential energy. So the total amount of initial energy equals the total amount of final energy. Then what I can do is, from how these terms are, and remembering that when I have a delta E, for example, or a delta something, that means it's final value minus initial value. This means that, well, if the final energy equals the initial energy, that means E final minus E initial, or delta E, has to be 0. And then similarly, that means the total change in potential energy plus how much the kinetic energy changes also has to be equal to 0. So what this term here tells us is that here we looked at this system in terms of the ball itself being the entirety of our system. And then the external thing to that, the force due to gravity, caused its kinetic energy to change. What we've done here is we've rewritten this in terms of, hey, maybe instead of treating the gravitational force as being something external, maybe we can treat the Earth and the ball as some sort of entire system. And then knowing where the ball is relative to the Earth, because that's what this term here would mean. It tells us a height relative to, some position. relative to the Earth. Maybe by now talking about this system in terms of the ball and the Earth, we can replace our discussion of the force involved with just a discussion of what would have been the amount of energy necessary to take some object from some place and then place it somewhere else. So we don't have to talk about the force anymore. We can literally just say the object was here. Later on, it's over here. We can associate a certain amount of energy with being here. We can associate a certain amount of energy with being up here. And it turns out that by just knowing those amounts of energy, or having a way of calculating those amounts of energy, that then tells us how the other energies in the system, in this case the kinetic energy, how it would have had to have changed in order to go from moving this here, having this here, to being over here. One final note on how to interpret this is that we can say here that now that we've taken the force of gravity and the Earth and the ball and we've made it all our system, remember when it comes to talking about work, the work is the amount of external forces, or is associated with the amount of external forces acting on the system. Now that the Earth and the ball are in our system, all the gravity is inside the system. So there's no more external work. So this whole expression here, just like I use some little asterisks here to denote that these are different work expressions. In this new way of looking at this system, now we know that the amount of external work here is 0, because now the gravity that was exerting the force is inside my system. But now, if I have the Earth and the ball and gravity all in, then that means there's nothing outside the system, and so therefore there's no external work. And when there's no external work, the total amount of energy is the same in my initial condition as it is in my later condition. This is what we call the conservation of energy. Total amount of energy in our closed system, in our complete system, if there's no external work, no external forces acting on it. Unless I was saying that. Yeah, so the total amount of energy in the initial and final is conserved. We're going to be able to make use of that because we're going to look here at systems where we're going to have some system in some certain configuration and pieces are moving around. We're going to account for how fast all the pieces are moving. We're going to account for how all the pieces are configured. And then we'll be able to just say, oh, at some later time, now the thing is located maybe somewhere else. That means we'll automatically have a way of solving for, well, how fast would it have to be moving? Or maybe if we know how fast it's initially moving and where it initially is, and later on we know it's moving this fast, well, where would it have to be located? This gives us a relationship because we'll know that the total amount of energy we started with has to be the total amount of energy we ended up with. And we would just use a formula like this to determine how the system would have to be behaving given that statement is true.